Guys, so today I'm going to be going over series and parallel dielectrics and how to treat each. So first, let's start off by considering two dielectrics in between a set of parallel plates, arranged horizontally like so. And so when you're thinking about these types of plates, how you can really think about it is a current flowing from the positive side towards the negative side, right? So this way. And when you think about it that way, you can see that this setup here is almost like a circuit. Some current is going to go through this dielectric and some current is going to go through this dielectric. And so it's going to resemble this type of circuit, which of course is a parallel circuit. And then for another type of circuit that we're going to consider is of course series. And so looking at what a series dielectric might look like, we could come to this conclusion because the current is going to have to flow through all levels of the dielectric, where the dielectric is acting almost like a capacitor or a resistor here. And so when we think about a circuit then, if we were going to draw it, we could draw it this way. And so when dealing with these dielectric questions that we're going to do, it's important to keep in mind our rules for series versus parallel. And so of course we're going to need this little chart here, and specifically with regards to capacitance, because that's the one that we're going to be looking at in these example problems. Okay, so for our first question here, I'll pull it up and let's read it. As shown, three square metal plates A, B, and C, each of 12 and then centimeters. Here's what I meant to say, but I forgot to do it, so I just put a little note in there. On a side and 1.5 millimeters thick. The plates are separated by sheets of paper 0.45 millimeters thick and with the dielectric constant 4.2. The outer plates are connected together and connected to point B. The inner plate is connected to point A. Show the charge distribution on the plates if A is maintained at a positive potential with respect to B, and what is the capacitance between the points A and B. Okay, so that was a lot of information. So first let's just take a moment to look at our diagram here and think about what's going on. And so one thing that helped me when I first approached this problem was to think about the diagram in 3D. So here we have our paper, right, going through three metal slabs. So each of these are independent metal slabs intersected by the paper dielectric, right? And then those metal slabs are also connected to circuits here. At point A and point B. And A and C are both connected to point B, while the metal plate B is connected to point A. And the other really important thing to note here is that it says three square metal plates. And so even though it doesn't look like it in the diagram because I haven't drawn it exactly to scale, this side length here is actually the same length as this side length here. They're both 12 centimeters long. And so with that, let's get into thinking about the charge distribution on the plates. So A is positive, they've told us, and B is negative. And so thinking about that, that means that the charge on this plate is also going to be positive, right? Because what other charge would it be? If it was negative, that charge would have to have somehow got to this point. But A is actually closer and connected to point B. So the negative charge isn't going to flow through this wire and then flow to here just yet, because they're just asking us for the charge distribution, the net charge distribution. And so that of course means that A must be negative and C must be negative by that same logic, because once again, how would a positive charge get there just yet? Because we're just talking about it as the net charge before any current has flowed or anything. And so I'm going to undo that just to clear up our diagram. And so we need to think about how we're going to find the capacitance now that we've determined the charge distribution on the plates. And so you may say, well, I know that the capacitance for parallel plates is given by C is equal, and then kappa A epsilon naught over D, right? Where kappa is our dielectric constant, A is the area of a singular parallel plate, epsilon naught is a constant, and D is the distance between the plates. But now you're going to say, okay, well, I got a lot of information here. How do I know exactly what to use? And so first let's start off by calculating our area for the parallel plates. So the area for our parallel plates is simply going to be 12 times 10 to the negative 2, because we need to convert from centimeters into meters here. And then we can just square that because, like we said, they are square metal plates. And so that's going to give us an area of 0.014 0.44. And then that's going to be meters cubed, right? And so we now know our area. We know this because it's a constant. Our kappa is given to us as 4.2. And the distance between the plates here is 0.45 millimeters because that is the thickness of this plate here, right? And so if I want to label all the dimensions on the diagram here, you can see I've labeled 0.45 millimeters as the width of the dielectric, and then these side lengths as 12. And then further, I've also labeled the thickness of the actual metal slabs as 1.5, and then that should be millimeters. Sorry, guys, not 1.5 meters. And so that's going to be 1.5 millimeters. Yeah, and so this is our area of the plate, so we know that. And then we know the distance also because that is 0.45 millimeters. And so we don't actually need to use this 1.5 millimeters thick. That's just thrown in there to make you think about, do I need to use the thickness of the plate or the thickness of the dielectric? But the formula here, this is the thickness or the distance rather, separating the parallel plates, which we are treating each of these metal plates as a singular parallel plate. And so you may say, okay, but I have 3 plates here, so how is that going to work for this formula? And so the answer to that is that we need to treat this system here as a parallel circuit setup. And so that means that our capacitance, our equivalent capacitance, our C sub EQ, is equal to the sum of the capacitance of each of these pairs of parallel plates. And so this parallel plate and this parallel plate, and then this parallel plate and this parallel plate. And you may also say, well, oh, my C disappeared, I'll just draw that back. You may say, how do I know that this is arranged in a parallel formation? And so from our previous explanation, if you didn't quite catch that, what's happening here is because the current is being split, the current is going to have to go from one of these terminals and then go through here, and then it's actually going to be brought back here. So it's going to flow like that, and that current path reminds us of a parallel plate or parallel circuit. So that's how we know to use this formula. And so then thinking about that, we know that these parallel plates here are actually going to have the same capacitance because all of the numbers are the same. The dielectric is the same, the area is the same, the constant's the same, and the distance between the plates is the same. So we can just write this as 2 times our C, which is over here. And so to calculate our C now, let's simply go 2, or rather our kappa 4.2 times the area, which is 0.0144, times our epsilon naught, which is 8.85 times 10 to the negative 12, and then all over, I'll make that line a bit better there, all over 0.45 times 10 to the negative 3. And so that's going to give us a capacitance for a singular set, for instance, A and B, or B and C, of, I'll just make that C a bit clearer, of 1 times 10 to the negative 9 farads, which are the units of capacitance. And so then just multiplying that by 2, that makes our CEQ equal to 2 times 10 to the negative 9 farads, which is also equal to 2 times 1 times 10 to the negative 9. Okay, so that's our answer for this guy. Okay, so for our second question here, let's read it. A parallel plate capacitor is made from 2 plates 12 centimeters on each side and 4.5 centimeters apart. Half of the space between these plates contains only air, but the other half is filled with plexiglas, which as I found out is spelled with 1s actually, of a dielectric constant 3.4. An 18-volt battery is connected across the plates. Okay, so let's take a second to consider our diagram first. So what we have here are 2 parallel plates, here and here, with plexiglas on one side and air on the other. And one thing that I was confused about was why there's only plexiglass on this side as opposed to having drawn it in a horizontal stacked position, and really like having plexiglass up here and then air down here. And really all that I can say is that I hope the question on a test or something would specify that a bit more clearly for us. But this is how you get the correct answer according to the textbook. And so I'm just going to sketch this in 3D now so that we have a bit better idea of what's going on. I wouldn't necessarily sketch this on 3D on a test though. This is just so that we can help understand a bit more what's going on. And so looking at this, we can see that here, right, we're going to have current going from the positive terminal, and then it's going to flow either across plexiglass or across air, and then into the negative plate. And so that should remind us of a parallel plate circuit because it's going through the dielectric and the air here, right? And so thinking about that, we're going to need to treat this as a parallel system. So we can say that the capacitance is, the equivalent capacitance is equal to the sum of the individual capacitances of both the plexiglass and the air. And so thinking about that, we're going to need to use our formula, of course. C is equal to, and then kappa A epsilon naught over D. And so we have kappa for the air because that is simply 1, and then we know epsilon naught because that's a constant. And then the distance between the plates was given here as 4.5 centimeters, so we know that. So we just need the area. And so the area of our plates is going to be equal to 12 times 12 divided by 2. And the reason that this is divided by 2 is because our air here only takes up half of the plate. So we're going to need to divide that by 2. And then thinking about that, well, not thinking about it, crunching the numbers, actually, it's going to give us 72 centimeters squared, right? And so that's our area. And so I'm just going to clear this up here so that we have some room to actually write our numbers in. And so then that is going to be kappa, which is 1, so I don't even need to write it, times our area, which is 72 times 10 to the negative 4, and then times the distance between the plate, or not the distance between the plates, sorry, the constant, which is 8.8 times 10 to the negative 12, and then all over a distance of 0.0045, right? And so I'm going to clear that once again, but if you crunch the numbers on that, what you're going to get, or what I hope you get, because this is what I got, is going to be 14.16 times 10 to the negative 12 farads, which I have no idea what this actually quantifies to in real life, but that's the value that you should get. And so now we're going to need to figure out, oh, and I should write that this is for air. And so now I'm going to need to figure out the capacitance for plexiglass. And while we could use our formula here of equaling the kappa times A times epsilon naught all over D, a shortcut that we can actually take, and it's not much of a shortcut, but it still is one, is to actually just multiply by our dielectric constant, because here the area, the distance between the plates, and our constant is all going to stay the same. So this is all going to stay the same. We just need to multiply it by this k because our k in the last question was 1. So essentially we just had this, and now we just need to multiply it by k. And so doing that, I'm just going to clear up some space once again for us to do that. And so what I'll write for that then is that C of the plexiglass is equal to 3.4 times 14.16 times 10 to the negative 12. And so then, of course, for our equivalent capacitance, that means that we're going to have 14.16 times 10 to the negative 12, and then plus 3.4, I'll write brackets instead, times 14.16 times 10 to the negative 12. And so then I'm going to clear up some space just so that we have room to write our actual answer here. And so our equivalent capacitance is then going to be equal to 62.3 times 10 to the negative 12 farads. And then that is our answer for the first question, or for the first part of that question, A. And so for the answer for the second part of that question, B, it's pretty simple, and we actually do part of it in C, or do it in a different way in C, so I just skip that. So let's move on to part C here, and I'll just keep our answer. It's always a good idea to keep your answer from the previous section, just in case you need that. So here I will remove that. And working on C now, we need to consider how we're going to treat it if the plexiglass is removed. And so if the plexiglass is removed, what we're actually going to have is just two air capacitances in between the parallel plates. And so we can still say then that our CEQ, I'll write it as prime for our new CEQ, is equal to 2 times C of our air, because we essentially just have two air capacitances that are affecting our overall capacitance here. And so then we can just write that CEQ as equaling 2 times the air capacitance, which is 14.16 picofarads, which is just times 10 to the negative 12 in another way, which means that our new CEQ is then going to be equal to 28.32 picofarads. And so that is our answer for the second part. And I will move that over and then clean up the board. Okay, so there is our CEQ. So now we're going to want to calculate the energy stored in the capacitor. And the energy stored in a capacitor is given by U is equal to a half times the capacitance times the potential squared. And so we know that the capacitance, we know that the equivalent capacitance of this whole system when there's just air is going to be 28.32, and then the potential across it is going to be 18 because the battery is still present there. And so if you want to think about it, you could imagine a battery being connected like so, and then squared, and so that will give you a potential energy of 4.6 times 10 to the negative 9 joules. So here we have a parallel plate capacitor with square plates 8 centimeters on each side and 3.8 millimeters apart. The space between the plates is completely filled with 2 square slabs of dielectric, each 8 centimeters on a side and 1.9 millimeters thick. One slab is Pyrex glass and the other is polystyrene. If the potential difference between the plates is 86 volts, how much electrical energy is stored in the capacitor? Okay, so first let's start off by drawing a diagram here. So we have our polystyrene and our Pyrex. Again, you don't need to draw this in 3D if you're in rush on an exam. I've just drawn it for our understanding. And then we're going to label some dimensions here. And so our first question is this a series or parallel example? And big hint, because the other two we did were parallel, this one is likely to be series. But the actual logic behind why is because current, if it comes through the top, if the top is positive like this, and the bottom is negative, what's going to happen is current is going to have to flow through both the polystyrene and the Pyrex. And that means that it resembles a series circuit, which means that our series rule of capacitance equaling the sum of 1 over the capacitance of each individual section inversed is going to give us our equivalent capacitance. And that comes in handy because we know that to get the energy for a dielectric, we can use this formula. And we have the voltage, we know 1/2, and we're trying to get this guy, but we don't have the capacitance. So we're going to need to figure that out. And so to start with that, let's go to the math. And so we're going to need to write that the equivalent capacitance is equal to 1 over the capacitance of Pyrex, which we'll just denote with Py, plus 1 over the capacitance of the polystyrene, which I'll just denote with poly, all inversed, right? And so I can also write this then as equaling d, I'll make my d a bit better there, as equaling d over k kappa py a epsilon naught plus d over kappa poly a times epsilon naught, and then all of that inversed again. And so I'm going to take out some common factors here, because if you look, my d, a, and epsilon naught are all actually common to each term, so I can take those out, and I'll just make a bit more space here. So I will now be writing over here. So I will now be writing this as taking my d, not my kappa, sorry, my area of a single plate times epsilon naught, and then over 1 over kappa for the Pyrex plus 1 over kappa for the poly, right? And so that is going to give me my equivalent capacitance, and so putting some numbers to that, I can then write, my bracket went off the page, is equal to the distance between the plates, and we're going to treat this boundary here as a plate, right? Because that is going to be you could call that an exchange for the current when it's flowing through. It's going to change mediums there. So that is the distance between each capacitance set, I guess, between the plate and the polystyrene and between the Pyrex and the other plate. Or you could view it as between these two and then these two, however you want to think about it. And so we're going to write 1.9 times 10 to the negative 3 over the area, which is 8 times 10 to the negative 3. And that's going to be a curved bracket squared, and that's just simply from these numbers here and this number here. And then multiplied on the bottom again by 8.85, the constant times 10 to the negative 12. And I'm going to extend this line. And then we're going to need to multiply that by 1 over kappa, which is 4.7 for our Pyrex, and 1 over 2.6 for our poly. And so then taking all that and inversing it, I'm going to clear up the board here. We can write that our CEQ, punching that into our calculator, is 4.9 times 10 to the negative 11 farads. And we wanted the energy, so we're going to write U is equal to a half our equivalent capacitance of 4.9 times 10 to the negative 11, multiplied by our voltage squared, which is 86 squared, giving us the total energy stored as 1.84 times 10 to the negative 4 joules. And I'm just going to box that answer to make it look nice. And so that's our last question for today. Hope you guys enjoyed.